Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky. This week in astronomy: dark matter influence on planets, lunar dust, and Sagittarius sea magnetic forces. Dark matter's hidden influence on planets. Dark matter is one of the most perplexing concepts in modern cosmology and physics, existing on the frontier of our understanding of the universe. Scientists do not know exactly what it is or how it fits into the established framework of physics, but its unseen mass plays a critical role in shaping the cosmos. Astronomers are certain of its existence due to the way galaxies rotate, the gravitational lensing effects it produces, and its influence on fluctuations in the cosmic microwave background. Despite these indirect observations, dark matter remains elusive, and researchers continue to explore new methods for detecting it. A recent study suggests that there might be another way to observe its presence, one that involves planetary physics. The study, titled Dark Matter S Pins the Planet, is available on the AR-14 preprint server. The research was led by Haiho Shi from the Xinjiang Astronomical Observatory at the Chinese Academy of Sciences, with co-authors from other Chinese research institutions. The authors emphasize that dark matter makes up approximately 85% of the universe's matter content, as confirmed by numerous astrophysical and cosmological observations. However, its fundamental nature and composition remain unknown, indicating the need for physics beyond the standard model and general relativity. The study builds on previous research suggesting that dark matter can be captured by planets, a process known as dark matter planetary capture. According to this idea, the gravitational pull of planets can attract dark matter particles, leading to their accumulation in planetary interiors. The physics behind this phenomenon are complex, and researchers are still working on estimating the density of dark matter inside planets. So far, they expect it to be extremely low, making it challenging to detect. There are multiple hypotheses regarding the nature of dark matter, including the possibility that it consists of primordial black holes, axions, or weakly interacting massive particles, WIMPs. Other candidates have also been proposed. Unlike previous studies that have focused on dark matter's properties on microscopic or cosmic scales, this research examines its effects on a planetary scale. The authors suggest that planets can act as long-term probes for detecting dark matter, as they have been interacting with the surrounding dark matter halo for billions of years. These interactions could produce cumulative, observable effects, such as changes in planetary temperature, rotational dynamics, and atmospheric properties. The core idea behind dark matter planetary capture is that as dark matter interacts with planetary matter, it deposits energy into the planet. While dark matter does not interact with baryonic matter in the conventional sense, certain quantum effects, such as quantum tunneling, allow for interactions. These interactions can lead to increases in planetary temperature and rotation speed. Scientists have now developed a new method for detecting these effects. Beyond the fundamental physics, the presence of dark matter inside planets could have implications for habitability. If dark matter heating alters thermal conditions, it could impact the stability of liquid water and the evolution of planetary atmospheres. This could influence the potential for life on exoplanets in ways not previously considered. When dark matter particles enter a planet, they undergo processes such as scattering, capture, and annihilation. Scattering events transfer kinetic energy to planetary material, generating heat. The same occurs when dark matter particles annihilate. The resulting temperature increase depends on the amount of dark matter entering the planet, and the energy deposited can also accelerate the planet's rotation. The researchers applied their model to 15 confirmed exoplanets, including notable ones like 55 Cancri d, Lippershey, and Epsilon Eridani b, both of which have drawn significant interest from scientists. Additionally, they tested the model on Jupiter and Earth. Their findings suggest that the energy supplied by dark matter heating is not fully converted into temperature. Instead, it is distributed based on the planet's intrinsic characteristics, such as mass and radius, as well as its current conditions, including temperature and angular velocity. According to the study, Earth is not immune to dark matter capture. The researchers predict that dark matter interactions, combined with the sun's heating, will result in a surface atmospheric temperature increase of approximately 0.015 K over 100 years and 0.15 K over 1,000 years. While this heating effect is small, it is still measurable. Dark matter heating may also contribute to an increase in planetary rotational velocity, though distinguishing this effect from other influences, such as tidal forces and seismic activity, is more challenging. For Earth, the researchers estimate that dark matter heating will accelerate its rotation period by about 12 seconds over a century. Over a millennium, this effect could accumulate to 120 seconds. These are substantial changes, and the authors suggest that ground-based measurement techniques should be able to detect them. A deeper understanding of these effects could have significant implications for exoplanet research, particularly in assessing habitability. As humanity searches for habitable worlds beyond Earth, the impact of dark matter on planetary rotation could become an important factor in evaluating the potential of exoplanets to support life. This research represents an intriguing step toward incorporating dark matter into planetary science and highlights the profound, yet still mysterious, role it may play in shaping worlds throughout the universe. Electrodynamic shield fights lunar dust. Lunar dust presents a formidable challenge for human exploration and long-term operations on the Moon due to its highly abrasive and electrostatic nature. It adheres to any charged surface, posing risks to spacesuits, hardware, and even human health. The fine, jagged particles can infiltrate equipment, degrade materials, and cause significant wear over time. Exposure to lunar dust can also pose respiratory hazards, making its mitigation a crucial aspect of sustaining human activity on the lunar surface. To address this issue, NASA has developed electrodynamic dust shield technology, which utilizes electrodynamic forces to lift and remove lunar dust from surfaces. This innovative approach has demonstrated its effectiveness in clearing regolith from critical components such as glass and thermal radiators. The activation of EDS technology successfully removed dust accumulation, proving its potential for protecting vital equipment in lunar and interplanetary environments. The successful demonstration of this technology represents a major step toward ensuring the longevity of space missions by minimizing dust-related hazards. Its applications extend across a wide range of surfaces, including thermal radiators, solar panels, camera lenses, spacesuits, boots, and helmet visors, all of which are susceptible to lunar dust contamination. By preventing dust buildup, EDS technology enhances the functionality and durability of essential systems, supporting NASA's Artemis campaign and future deep space exploration efforts. Developed at Kennedy Space Center in Florida, the electrodynamic dust shield was funded by NASA's game-changing development program under the Space Technology Mission Directorate. This advancement not only addresses a critical issue in lunar exploration but also lays the groundwork for broader dust mitigation strategies in space environments, ensuring safer and more sustainable operations beyond Earth. Magnetic forces and star formation in Sagittarius C. Sagittarius C is among the most extreme regions of the Milky Way. Located about 200 light-years from the supermassive black hole at the galaxy's core, it consists of a massive and dense cloud of interstellar gas and dust that has been collapsing for millions of years, forming thousands of new stars. Recent observations using NASA's James Webb Space Telescope have allowed scientists to study this region in unprecedented detail. led by astrophysicist John Bally from the University of Colorado Boulder, along with Samuel Crowe from the University of Virginia and Ruben Fedriani from the Instituto de Astrofísica de Andalucía. The research offers new insights into the complex mechanisms at play within the central molecular zone of the galaxy. One of the long-standing mysteries about this inner region is why fewer stars are forming than expected, despite its high density of interstellar gas. The study suggests that powerful magnetic field lines thread through Sagittarius C, creating long and bright filaments of hot hydrogen gas that resemble strands of spaghetti. These structures could be influencing the rate of star formation by slowing down the collapse of gas clouds. According to Bally, this part of the galaxy has the highest density of stars and massive clouds of hydrogen, helium, and organic molecules, making it a key region for understanding extreme astrophysical conditions. He and his colleagues published their findings on April 2 in the Astrophysical Journal as part of an observation campaign proposed and led by Crowe, a fourth-year undergraduate student recently awarded a Rhodes Scholarship. The Webb telescope's images reveal Sagittarius C in a way never seen before. Crowe emphasized that due to the presence of strong magnetic fields, this region has a fundamentally different structure compared to other star-forming areas located farther from the galactic center. The research highlights the violent processes involved in the birth and destruction of stars. Stars typically form within molecular clouds, which are dense regions of gas and dust. The closest stellar nursery to Earth is the Orion Nebula, where clouds have collapsed over millions of years to form clusters of stars. However, star formation eventually disrupts itself as newly formed stars emit intense radiation, which disperses the surrounding material, preventing further star birth. Bally and his team also studied the young protostars in Sagittarius C, analyzing how they eject radiation and shape their surrounding environment. One of the most striking features of the region is its bright filaments, some extending for several light years. These filaments are composed of plasma, a hot, ionized gas, and their discovery was unexpected. Fedriani, a postdoctoral researcher involved in the study, described the finding as completely serendipitous. The presence of these filaments is likely tied to the region's strong magnetic fields. Gas movements near the supermassive black hole at the galactic center may be stretching and amplifying these fields, influencing the structure of the plasma. Bally pointed out that the Orion Nebula appears much smoother because it exists within a much weaker magnetic environment. While the inner galaxy is known as a major site of star formation, observations suggest that it should be producing far more stars than it actually does. The study supports the idea that magnetic forces could be preventing the gravitational collapse of molecular clouds, thereby slowing the birth of new stars. Sagittarius C itself may be nearing the end of its active star-forming phase. Its young stars have already dispersed much of the molecular cloud that sustained them, and in a few 100,000 years, this stellar nursery may disappear entirely.